Good morning, good afternoon, and good evening to some of you. Welcome to this webinar on CRIDA applications in California. We will give you an overview of some of the ongoing activities as a case of CRIDA and as part of the CRIDA online training course. So my name is Koen Verbist, and I'm the program specialist for the UNESCO Regional Office for Southern Africa related to the natural science sector. Just to start this webinar, we'll just give you a few housekeeping rules for this webinar. So in any case, if you have any questions or issues you would like to raise, you can use the chat option, which you find on the bottom of your screen, as well as if you have any specific questions, you can use the Q&A box where we can directly answer the question, or we can also raise the question during the Q&A session. So during that session, we will of course identify some of the questions that were already posed in the chat box or the Q&A box, and we will give those questions to the presenters. But also, if you would like to ask your question directly, you can raise your hand, and then we can unmute your microphone so you can ask the question yourself. So you have those two options. All right, so before we start, we just wanted to guide you through the program of today. So I'll just give you a short overview of where we are with the course, and I'm actually quite happy with all the participants that we have from all over the world. So I'll just give you an overview of where the people are coming from the course participants. Then we'll follow with a longer session looking at the CRIDA implementation in California, which is of course the bulk of the objective of today. And we'll be joined by Romain, Maendly, and James Wieking from the California Department of Water Resources. Finally, we also will find time for addressing some of the questions you may have related to the course. And some of my colleagues from Deltares, Agua, and US Army Corps of Engineers will join us today if you have any specific issues you would like to raise with the course developers. Of course, we can see if we have enough time today. If not, we can always extend for another session later down the road when we see that demand is quite high. And then, of course, we'll finalize this webinar with a few remarks. So just without delay, I would like to go to the course overview, and I'll just ask my colleagues maybe to put on the next slide. Thank you. So in terms of course participation, we're quite happy to report to you that about more than 700 people have joined the CRIDA course so far, and you can see the distribution globally is quite clear, and we see participants from both from Asia, Africa region, Europe, US, as well as Latin America. So I think this is for a first starter for the course is quite impressive in terms of attendance and interest. Today, we will probably only have a portion of those participants joining in the webinar. We will also make sure that this webinar is available for consultation in the course in the next few days for those who cannot follow or not able to follow the full session coming forward. So in terms of distribution, I think it shows that from all continents there is interest to learn about and maybe apply some of the concepts that are introduced in this CRIDA learning course. The next slide. So you can see that there's quite a lot of representation from this region, which is the Southern African region, with several countries, but we also see countries such as Chile, Peru, represented from Latin America, as well as, of course, from United States, but also from Sri Lanka, India, and some other countries are quite well represented, also from other parts of Africa. Next. In terms of distribution, we just share with you that quite a lot of people joined, and we're happy to see quite a good distribution in terms of gender. Of course, we would like to keep that as much as close as possible to 50% of each. As well as we're looking at different education backgrounds, which helps us understand how we should pitch the course in further events and how we can maybe improve on some of the elements that we have currently put in there. And I'm just finally, I'll just share you the age distribution, so showing that in terms of course participants, we have mainly people from 25 to 35 years old taking it, but also from, let's say, 15 years old until over 41 years old. So I think it shows that there is a big group of people who are probably early careers that are interested in learning about these concepts, and we would like to ensure that we can keep working together to identify ways to support your work going forward. That's just a very short introduction to the course and how far it's going. I think we're almost at about 50 persons that have finalized the course and have received their certificate. So congratulations for that. And if you have any issues that you find, you can always reach us on the email that is available on the platform. And of course, through the discussion forums, you can raise any questions related to the content of the course. So without further delay, I just want to introduce our speakers of today. I would like to introduce both Romain Maendly, and James Wieking, who are both senior water resource engineers of the climate change program of the California Department of Water Resources. So Romain and James, please, you have the floor for this next session of the webinar. Thank you. Maybe you can just give a short introduction first.
Yeah, thank you, Kern, for inviting us to present. Let me pull my presentation real quick, and I will start. And I have some. Where is it? Oh, that was fine before. Share computer sound. Okay, I'm just going to share my screen. So hello, good morning, good afternoon, everybody. My name is Romain Maendly. I'm a senior engineer with the climate change program of the California Department of Water Resources. And my colleague Jim Wieking is a supervisory engineer working for the Division of Planning. And we are very happy to join this session today. UNESCO has always been like, a point of reference, at least for me, from my career. So it's a pleasure to be here today. We're going to try to cover what we're doing in California, kind of case studies that we're working on related to CRIDA. And we're going to start to talk about the California water management overview to kind of give you a perspective about what's going on in California, what are the challenges that we have. Then I'll present the Climate Action Plan Phase 3 related to the Stillwater project. Is a big aqueduct. We're going from the northern side of California down to the south side of California to provide water not only for urban area but also for agricultural need. And then we'll talk about the pilot CRIDA application that we're doing with the Merced and Turlock watershed studies. I want to mention up front that is not solely James on my work. It's a big team. It's people who have been working on CRIDA before. We were there in our position, and people who also continue to work on CRIDA. The Department of Water Resources is not the only one in the state of California to use CRIDA. There is the San Francisco Public Utility Commission who is using it. There is other state agencies who started to apply it. And so we're just, a part of the small community was growing in California to try to apply it, and with some success. So California is it's a Mediterranean climate region. We have in the northern side of California, which is very, we have a lot of some precipitation, much more precipitation than the south. And this precipitation is really extreme and variable. So we have period of droughts of like 2, 3, sometimes 5 years droughts, as well as sometimes flood. Like in 2017, we had a big flood who created a lot of challenges in the Central Valley. You can see that most of the water is being captured along the Sierra Nevada. That's the kind of the purple on the back on the eastern side of the state. And this water is really, a mass of snowpack was accumulating from November down to February, and will start to melt over time over the year. historically the precipitation occur really between November and March. Also, I want to point out that we have the Centrale, which is this big mass, like area in the center of California. That's very much like the breadbasket of the state of the United States, where we grow all kind of crops from oranges to almonds to strawberries and so on. So it's very a mixture of like high density population as well as heavy agricultural industry. Related to climate change and the effect in California, as I mentioned earlier, we have the Sierra Nevada, and these Sierra Nevada are really helping us to provide water throughout the year. As I mentioned earlier, the raining season stops around March, April, and so we rely heavily on the snowpack to provide water for the rest of the year until the end of November, when the temperatures start to drop again. And so with climate change, one of the major challenges that we're going to have is an increase in temperature on the Sierra Nevada, which is going to really shift the hydrologic cycle. Then there is also the change in precipitation pattern. As you know, certainly as temperature increase, we have more vapor transports coming from the Pacific Ocean. And so we have this extreme precipitation happening during the winter. And instead to have snow accumulation, then we have mostly precipitation, which is creating a lot of runoff. And so some of our rivers are really overwhelmed by this extreme precipitation. And finally, one of the big challenges that we have too is that most of the coastline of California is very important, not only for tourism, but we have a delta, and through this delta we are doing a lot of water management, and 50 centimeters of water of sea level rise is expected by the end by the mid-century. And so you can imagine, similarly to the Asian country and Egypt, where you have sea level rise and salt intrusion, what kind of damage it can create to the crops and also the water quality in general. So big challenges. As I mentioned in my first slide, most of the water comes from the north. If I were to separate California in half, and you can see the half full right in between the Sacramento River and the San Joaquin River, that's where the two rivers meet the delta and go into the Bay Area. You can see that 80% of the runoff come from the north, while only 20% of the runoff is on the south. And so cities like Los Angeles, San Diego, even Fresno rely a lot on groundwater and export water. And when you talk about export water, 1/3 of the demand is up on the north, and 2/3 of the demand is on the south. And so that creates a lot of challenges to bring water from the north to the south. And we have a system of aqueduct and deliveries to really move this water from California to bring the water to the cities and the farmland near Fresno. So the California water supply system can be divided in, if I were to do a water budget and looking at how the water is distributed in California, approximately 30%, 32% is for in-stream flow, environmental flow requirements. Mostly on the northern side of California. We have some stream on the south side, but it's really these tributaries along the coastal line who are in-stream environmental flows. Then you have local projects, and local projects can be for local cities who have developed their own conveys, like San Francisco or Oakland, but also the Mono Lake. If you look on the map on the left side here, you can see that there is some a long aqueduct who's going from Mono Lake down to LA. That was one of the first aqueduct in the States. And they are mostly for water supply and urban consumption in general, with some local ag consumption. Then you get the groundwater. That's 21% of our consumptions, and it's mostly in the Central Valley where the breadbaskets of the United States is found. This groundwater has been legislated, and I will talk a little bit more in my next slide. But this groundwater is mostly used for agricultural needs in general. Then you have the federal projects in yellow, who brings in conjunction with like the state projects. You can see that we have some federal projects in the north side who bring water to the farmland, and also like in the Central Valley a little bit more like federal projects. We have some Colorado project along the Colorado River will bring water to the San Diego area. And finally, we have the state projects, and that's really the responsibility of the Department of Water Resources. And that's bringing water from the northern side of California through a system aqueduct down to the southern side of California to LA and Los Angeles and San Diego. So California water management, it's complex. We're moving water a lot, and there is 1,500 district managers who are not only managing water supply, but also water quality, flood. And then just recently in 2014, we finally had a regulation about groundwater management as well. Before it was really proper to the landowner to like pump quantity of water that they needed for the crops. So we passed a law who regulates groundwater management, and that created a new set of like set of agencies to manage this groundwater. So I'm not sure if like 1,500 is only like the supply, flood, and so on, but you can add another 300 entities just for the groundwater management. And on top of that, you need to think about like all the NGOs who are pushing for good reason for more water in our rivers, and they are all around California in general. So you're mixing different purposes, different needs. And often people have been working in silos in general. So I'm going to change gears now, and I'm going to talk about the State Water Project's Climate Action Plan Phase 3. The Department of Water Resources had developed this Climate Action Plan, which is divided in 3 phases. The first phase is really related to greenhouse gas emissions. So our own capacity as a department to reduce our emissions in general. The phase 2 is related to how do we approach climate change in our analysis. Try to develop some sort of consistency throughout the department. And it's going to be more and more important moving forward because we are not only managing water supply, but also flood and ecosystem needs. And so if we start to mix and match different processes on how to assess climate change, it's going to be harder and harder to have a cohesive standpoint on how we are going to deal with climate change moving forward. And in fact, the 2 pilot studies that Jim is going to talk about are related to that. And finally, this Climate Action Plan Phase 3 is really related to our own business. What the department is own infrastructure, facilities, and how we can cope with future conditions. So the State Water Project description is really a 30 storage facilities throughout the state, 700 miles of open canals and pipelines, and we distribute water to approximately 25 million California, and about 750 acres, 1,000 acres of irrigated farmland. So while it's only 3% of the water in California, his purpose is very important for the state. And the exercise we're doing here in this project is a 2-step process. First, to understand our vulnerability, do a vulnerability assessment of long-term or persistent hydrologic impact of climate change on the operation of the State Water Project. And secondly, to develop and implement an adaptation process to protect either our business operation assets. So we want to make sure that moving forward, the investment we're going to make for the Stillwater project are going to be a positive return on investments, especially in sight of change in precipitation, change in temperature, and sea level rise. One thing which is nice about the Stillwater project is that we only evaluate the water supply aspect. So we didn't take into consideration what would be the impacts of flood or a change in precipitation to the project. And so it's really water supply centric. So obviously we are here to talk about CRIDA. And if I look into the 5-step approach, where we're at right now is really at step number 3. The first step, it was to structure a collaborative process for vulnerability assessment. It's really our own business. While we are collaborating, we have contractors that we are working with, and we want to be transparent with them about the future of the Stillwater project. It's really our own, we maintaining these projects, and so there is not a big outreach to make sure that everybody is involved in the process but we're going to be as transparent as possible. So every document that we are releasing are publicly available. The second step has been already done. It's implementing a bottom-up vulnerability assessment, and that's what I'm going to cover mostly today related to the Stillwater project. The step number 3, we are currently formulating alternative plans. So we just released our adaptation plan for the Stillwater project, outlining the CRIDA process. And so the next step is going to be to create adaptation strategies that we want to evaluate from one another. Step 4 and 5 are still far away because let's do one step at a time and figure out what is feasible to implement on an adaptation standpoint first before to try to combine these adaptations from one another. So if you're familiar with the methodology that we use to assess climate change, most people use a top-down approach or a downscaling approach, where we use general circulation models. We downscale them to a local level. Then we run these scenarios through a operation and planning model. And finally, we do our conditional system performance projections. So we're trying to evaluate, what could be the future. We select maybe, 3 or 5 features, but it doesn't really cover the whole range of future conditions. So there is quite a lot of disadvantage, but in the same times, we need to recognize that's the best information available to evaluate climate change. So I'm not want to take away that the GCM are bad. I think that's the best information, but in the same time, the uncertainty behind them is very large. When you think about emission scenarios, when you think about downscaling methods, when you think about model selection or ensemble, and when you try to bias correct the information to historical data. On the top of that, every 5 years, you're going to have new information. We just, we starting to have new information about CMIP 6, and that's going to be the new information. And we're also using newer technique to downscale the information at the local level between BCSD, LOCA, and dynamic downscaling. Finally, I took a quote from Casey Brown, who is the godfather of decision scaling. Planner will always wonder if the result will be different, if different sets of projection or method were used, because each GCM will have their own prints. And so it's very hard to try to take a decision when you have so many choices. So we're taking a bottom-up or decision scaling approach, where we start with, it's pretty much like a stress test or a threshold analysis, where we constantly, systematically perturb a sequence of precipitation and temperature. We apply that to our system model. We create a surface response grid, and then we superpose the surface response with our GCM to be able to understand at what point or what is the tipping point of our system. When should I start to act at what point, I'm not satisfied with the response from my system from a future sequence of climatic conditions. So I will show you a little bit how that look like and what we have done. So here's a surface response, and I'm not going to go through like the whole model exercise, the calibration, and all the very technical information. I think the most interesting part is really the results and how to interpret the results and how do we move from there. So here's a graphic where the x-axis represents the change in precipitation from -30 to +30% of precipitation. The y-axis represents the change in temperature from 0 to 4 degrees Celsius. Each of these dots represents a sequence of hydrology from precipitation to temperature of the system. So if I look at the point 0, 0 right here, it's really the historical sequence of what we have experienced, the last 30 years. In this condition, in this scenario, what we have done with the Stillwater project is that we use the Paleolithic climatic information. So we're using 1,000 years of reconstructed information and run it through our system to make sure that we not only capture the annual variability, but the long-term droughts. The drought that we may have never seen or experienced, and make sure that our system can handle it. And then each of these dots represents another 1,000 years of model simulation, where we perturb the precipitation by 10%, 20%, and so on, homogeneously, and we change the temperature, the observed temperature by 1, 2, 3, 4 degrees Celsius. So we run these scenarios, and we are able to calculate the average annual Stillwater project deliveries. How much over these 1,000 years of data, on average, each of these data will provide an average of over 1,000 years of information. So that's how you look like. Very pretty. Blue is better. Orange is worst. The point 0, 0 show again historically what we were able to export or deliver historically. So we were at 2.71 million acre-foot of water per year. If you follow the trend, the black line, you will maintain the current performance of your system. Now, you notice that the direction of the line are a little bit diagonal to the right side. That means that if I increase my temperature, I will need to have a little bit more precipitation to be able to maintain the same level of performance. Let's say here I increase the temperature by 2 degrees Celsius. I will need to increase my precipitation by 12% to be able to maintain the same level of performance of my system. Another example here is if my system, in a future condition, my temperature was increasing by 2 degrees Celsius and my precipitation change will decrease by 10%. My system, the Stillwater project, we have a reduction in deliveries, and we'll only be able to deliver 1.9 million acre-foot of water per year. So that's nice, but it doesn't tell you really how the climate, this GCM, where we fall. Maybe I'm going to be at 2 degrees Celsius. Maybe I'm going to be at 4 degrees Celsius. So one of my colleagues had an ingenious way or novel way to approach it with Casey Brown, was to superpose the GCM on the top of the surface response. So here we look at the watershed in the Stillwater project, who contribute to the Stillwater project, and each of these dots represents one general circulation model projection. So you can see the range can, like by 2050, can go from 0.9 degrees Celsius up to 3.5. And same thing for the precipitation change, from -15 up to 25%. So if I were to do the binomial distribution, or look at the probability that may happen, the median will be right slightly wetter and definitely warmer at 2 degrees Celsius. and you can start to animate over time what it will look like. So you can see that the bubble increase as we move on time. And by 2050, we reach the 2 degrees Celsius. And by 2075, we are almost at, well, end of century, we are almost at 4 degrees Celsius. And the range of uncertainty on precipitation can be from one side to another. So that's a lot of uncertainty to deal with. The beauty of what my colleagues did was to superpose the surface response with like this cloud of future condition. And we are able to prognostic or give a probability of future condition. I think as water resources engineer, we really are savvy about probability on what the future will look like. And so being able to say there is so many chance or so much probability that my system will perform better, but there is so much probability that it will perform worse, and I really want to cut back on this risk that I may take, is very useful for like decision maker. So on the right side, I presented like a range of metrics of that we evaluate. We look at Orville April storage, Orville carryover storage, the winter net delta outflows, spring net delta outflows, summer delta outflows, and so on. And we're able to estimate if the system will perform less than the current performance. And you can see quickly that the two big metrics that really worried us the most are the Orville carryover storage, which has 95% chance to perform less than the current performance. And that's our kind of drought metric, right? Because you have this carryover storage to make sure that you protect yourself if next year you will have a drought. And so knowing that we're going to be more vulnerable to drought in the future is very frightening. The other one, which is also important for us as delivers of water, is the seawater deliveries, and we have 87% chance that we will deliver less water. Going back to the graph on the left, yet you still have a potential chance that you will get more water. You will be able to deliver more water, but the majority of the projection fall on the orange side. And so we need to be prepared for this case scenario. So the way that we are going to approach it is by, evaluate different adaptation strategies and see how far, in the short term as well as the long term, we can move the black line to the left. And also the question with my colleague at the department and my executive will be how much risk we are willing to absorb. Obviously, I may not want to try to capture the whole cloud. That may be too costly. But there may be some adaptations in combination that may allow us to get up to the median future conditions. And just for that, it will be useful to invest and strategically think about when do we need to invest. I'm going to change gears now. That was the seawater project. I'm going to introduce our pilot CRIDA application on Merced and Turlock watershed studies, and Jim will take over on the Merced study. So one thing that's as you saw earlier in my presentation, there is a lot of local entities in California, and often these entities are only in charge of one water sector. But we recognize that with climate change, we cannot just evaluate our own silo perspective. We need to really open our eyes and think about, the flood aspects, the ecosystem aspects, the water quality, the hydropower, and so on. And so the idea behind the Merced and Turlock watershed studies is figure out a way to really uplift local entities to absorb the uncertainty in the future condition, in future condition, and be able to take decision in the future. So these two pilot studies are in fact great because they are adjacent watershed from one another. And so we can compare the Merced study, which is really a single entity run by a single entity, versus the Tuolumne River watershed, which is run by multiple entities throughout the watershed. We are doing the two-step process, a vulnerability assessment first and an adaptive planning to evaluate the effectiveness of adaptation strategies. It's really CRIDA-like. There is definitely like the input from the NGOs early on the process, with a little bit more success on the Merced than the Tuolumne. And it's just the matter of the fact that the Merced has, we working with one entity, when the Tuolumne we had multiple entities, and as you increase the number of folks, it's getting a little bit harder. The different approach is that on the Merced we're using a similar approach than the Stillwater project, but it's paleoclimatic reconstruction of historical hydrology. On the Tuolumne, and I will touch on it on the next slide, is in an innovative stochastic weather generator that John Koszarski, the next speaker on the panel, can talk about it much better than me in general. But I think that's really the future on how we can combine the general circulation model with a systematic approach to perturb the climate. And also, like the purpose of the two studies are a little bit slightly different. On the Merced, we really focus on this adaptation strategy called flood managed aquifer recharge. When in the Tuolumne study, we are more interested about looking at the broader range of adaptation strategies, but also trying to understand the effect of the atmospheric rivers connected to the climate change effect in California. As I mentioned earlier, related to the precipitation, these atmospheric rivers, one atmospheric river can provide between 10 to like 30% of the available water over a year in California. And so being able to understand how these atmospheric rivers will change with climate change is very important. So I'm just going to talk about the weather generator and what it does, and the perturbation about it. That's just a teaser. I think hopefully next year we get invited again to present, and we may have like more information to like present. But at this point, I just wanted to point that, like, talk about the weather generator. So the weather generator is taking historical information on an annual, seasonal, daily, hourly time step, and create many simulated time series of weather data on precipitation, on temperature. The beauty of the weather generator is that we can perturb this weather, perturb the sequence of historical data by thermodynamic perturbation, which is the increase of the extremes, and also the dynamic perturbation with the intra-annual variability. In California, again, we are dependent of the Pacific Ocean. The Pacific Ocean create like these big atmospheric rivers. We may intensify themselves with the increase in temperature, and that's really the thermodynamic aspect. But in the same time, the Pacific Ocean is also like creating this weather regime of this blob who stay in place and don't transition to another weather regime. And so the dynamic perturbation can help us to understand how they may change over time. So on that, I'm going to transition to the Merced study and let Jim Wieking, my colleague at the department, talk about it. Jim, all yours.
All right, thanks, Roman, and thanks for having us here today. Thanks, Con. We're excited to be here. We're Department of Water Resources in California is using the CRIDA framework to advance a couple water management changes that we're hoping to see in California, and hopefully you'll pick those up as I describe the Merced River watershed study. We're calling it a floodmar reconnaissance study, and so next slide, just quickly what floodmar is, because Because of the need to get more water in the ground, it's a strategy to bring groundwater operations together with flood operations, specifically using high flows from rainfall or snowmelt for managed aquifer recharge. That's the simple concept behind it. We're looking at putting water on agricultural lands in the wintertime, or working landscapes, or natural managed lands. Next slide. What are we trying to accomplish? I mentioned a couple advances we're trying to make in California. First of all, this concept of floodmar, we're trying to try it out at the watershed scale. We're specifically interested in getting water managers to think at a watershed scale rather than at their smaller scales of their service areas. Romain mentioned the 1,500 water managers in the state, or water management districts in the state. We're using a vulnerability and adaptation approach. This is the CRIDA approach: climate vulnerability, and then adaptation. We're looking at floodmar, doing managed aquifer recharge. We have an integrated tool set. We like to call it a headwaters to groundwater analytic process. We're stressing multi-sectors. So we're asking flood managers, water supply managers, ecosystem managers, and groundwater sustainability managers now in this regulated groundwater era. And we're piloting these concepts. We're piloting scale, approach, analytics, and sectors to get water managers to do things a little bit differently in California. Next slide. So our climate change, what we're doing with climate change, we're exploring what might happen in a future climate with 30 climate scenarios, again, using the paleoclimatic reconstructed hydrology, 0 to 4 degrees Celsius, and minus 20 to plus 30% change in precipitation. Doing that, we can generate 100 years of hydrology. On the right is a similar graphic showing the response curve between with the temperature variation and the precipitation variation. And what you see there is that clearly the annual inflow to the main reservoir on the Merced River is mainly impacted by just changes in precipitation. Next slide. So what are the adaptations that we're looking at? Well, the adaptations include what we call level 1, level 2, and level 3. We're looking at can we get water into the ground using existing infrastructure and existing operations? And then we're going to also, in level 2, look at potential forecast-informed reservoir operations and maybe modifying the reservoir rule curve for flood and water supply operations. And then in level 3, we'll look at changing infrastructure a little bit, potentially maybe some new conveyance to get water to areas to do additional recharge. Next slide. We have a set of metrics that we're looking at to describe our results. We're wanting to, again, describe results in the different sectors. So we are describing flood risk. And if you click through these, Romain, water supply and ecosystems, you see there on the graphic some of the metrics that we're interested in looking at. And again, in 2 steps: first of all, vulnerability to climate change, and then assessing the benefits of the adaptive strategy of floodmar. Next slide. Here's some, how do we do that? We do that with an integrated model tool set, 2 rainfall runoff models in the upper left and bottom right corners, a couple of operations models, a statewide model on the far left there, and then a reservoir operations model on the Merced River. And then a groundwater model on the middle right that is an integrated surface water groundwater model. And then we have two recharge models. Those provide the interface between surface water and groundwater. And the recharge optimization model helps us to assess the ability to put water on agricultural lands specifically and maximize the recharge. And then down at the bottom in the center, a couple of flood models, a hydraulic model, and a damages model. So we're looking at those multiple sectors. We're trying to get these models are integrated in a way where we're working through a sequence of results for 30 climate scenarios and then 9 different adaptation strategies. So here's some quick look at some results. First, vulnerability. This is, kind of an old school approach, 1956 flood event, which is one of the major flood events there. One of the unique things of the Merced River is that it has never spilled in its history. So you can see that even in this really large flood event in 1956, we're able to maintain a flow of 6,000 CFS. If you increase temperatures, the duration of the curve just gets a little bit longer. But then if you start adding additional precipitation, with a 10% increase in precipitation, you see about a little over a doubling of peak flow, so you do have a spill. And then if with 10% increase and 3 degrees increase in temperature, you get about a 7 times increase in flood flows. And so that would be very difficult to manage in the current system because 6,000 is the maximum capacity of the channel downstream of that reservoir. Looking at adaptation, some of the adaptation results in the next slide. Here's a result for how we do in terms of getting water recharged into the ground. So what you're seeing here is a 100-year accumulation of recharge from both the river and then some adjacent creeks. The river is the green bars, and then the other colors are some smaller creeks that are supplementing the amount of water that we're able to recharge. Over 100 years, we're able to get about 4.6 million acre feet or 46,500 acre feet per year. And then in the next slide, what we show is kind of how that breaks down. We're actually able to recharge about a little bit less than half of the water through the canal. A little tiny bit in recharge basins. Most of the water is recharged on farm, and our recharge models help us identify which farms, which crops, what soil types are good for that. And then only about 8% of that water is we can't get into the ground when it's actually available. And then that gives you a total of, if you one more click, total recharge of about 4.3 million acre feet. And then the next slide shows where that water goes. If you run it into the groundwater model, you'll see that there's continuing overdraft. This is what's happening in California. This is why the new regulatory effort for groundwater came into be about 6 years ago. You can see that there's an accumulating overdraft in the basin that follows the surface water hydrology. That's about 5 million acre feet over 100 years without doing any managed aquifer recharge. And we can mitigate about a third of that with flood mar recharge. over the 100 years. And then in the next slide, we'll show where that water goes. So about a third of it improves storage in the basin. A little bit more actually flows out to adjacent subbasins who are also overdrafted, and so a little bit bigger holes in the groundwater basins nearby. Water is actually flowing to those nearby basins, and then a portion of the water also goes back to the streams, which we think is a benefit, an ecosystem benefit for those streams. And then a final slide. Go ahead, next slide. Thanks. That's just a quick overview of what we're trying to do, and again, using the vulnerability and adaptive planning framework to push some new ways of thinking in California. Thanks for your time. And I think we can do a little Q&A.
Good. I don't think we heard you. Good.
All right, now you should be able to hear me.
Yep.
Okay.
Yes.
All right, thanks for that. I was quite impressed and also learned quite a lot. For me, it was also a new case study. We see a lot of Q&A happening in the Q&A box as well as in the chat. So I'm trying to extract some of the questions specifically related to the presentation, while we also have quite a lot of questions related to CRIDA in general. So we may open that up for the next session where we go a bit more into general CRIDA questions. Arfa had a question related to local water, state water, federal water, and what it actually refers to. Even specifically about the management of that water. And then maybe related to that question, if you can imagine how to institutionalize those decisions in the last step of CRIDA, which of course is still down the road, how are you going to consider these different local, state, and federal governments institutes playing out in that phase?
You want to dig it, Jim, or you want?
Sure. So yeah, so California has the state of California and the federal government and local projects. So it's a combination of all those things, do all the water management responsibilities in California. And that's great on the one hand, but it makes it really challenging because bringing all those water managers together to make decisions to improve our water management sustainability into the future is challenging. And so one of the things we're trying to do with these studies is say, let's bring the water managers, that includes federal, state, local, and then also ecosystem managers together. Let's bring them together at a watershed scale and make decisions at that watershed scale rather than independently. We call that in kind of a siloed approach. And we're trying to get away from that, bring people together, make decisions together. And that's one of the things that we think the flood MAR concept does. It forces people to think at the watershed scale and in those all four of those sectors, water supply, flood, ecosystems, and groundwater specifically.
Thank you for that, Jim. Just a question, maybe more technically, some of the participants was really referring to learning a bit more about the flood operation, how you handle that.
You want to take that, Roman?
It's a
Yeah,
very general question, but go ahead.
so the federal government sets rules to make sure that we don't first of all that we don't raise the level in the reservoir to a high level that we're going to take a risk. And so most of the roll curve in general of the reservoirs are pretty flexible from March, April down to November, October, outside the rainy season aspect. And then we kind of they start to create more strict rules during the wet season to create some space behind the reservoir. So that's one of the first rule. And then the second rule is really how much can we release downstream on the safety level, because there is population downstream, and we want to make sure that and the whole set of levees, and so we want to make sure that these populations stay safe, and the assets behind the levees stay safe. And so we are lucky in California because we are able to predict up to 6 days pretty accurately, what is going to come to us. And before, it wasn't the case because we didn't have the satellites, we didn't have the radars, and all the technical information that we had, that we have right now. And so with all this information, we can start to relax slowly these rules of operation. And that's called FIRO, Forecast Informed Reservoir Operation. The Scripps Institute of California in San Diego has plenty of research on that aspect of how to predict atmospheric rivers, who can really help make the rule curves behind the reservoir more flexible. So that's the aspect on the flood side.
Thanks for that. We have 2 more questions for now. So please, if anybody has additional questions, please put them in the Q&A so we can actually address them. So David Poblete from Chile, he's requesting a bit more information on the related to the perturbation, in this case about the changes in precipitation and temperature. And each point represents only one simulation with those changes in precipitation and temperature. But also, are you also using ensembles of different simulations? So how do you apply the changes to the time series, just annual changes? Because you may also have uncertainties there that you may have to consider.
That's correct. And so right now, with the Stillwater project on the Merced study, we're using this paleolithic information. So it's a 3-ring reconstruction that we have done. We have pretty good information on the last 50 years of observed temperature on precipitation that we can derive runoff. And with the 3-ring, we are able to reconstruct a sequence of temperature and precipitation. Now, when we perturb the temperature and precipitation on the Merced on the Stillwater project, is really homogeneous change. So everything move by 10% of precipitation, or get reduced by 10% of precipitation. And you're right, that's sometimes an issue, because that's not necessarily what we're observing with climate change. We're observing a lot of change in thermodynamics aspect, where atmospheric rivers or extreme precipitation are becoming even more extreme, and smaller precipitation are becoming less intense. And so that's where the Trelawney study is focusing on. So far, I think it's really a good starting point as just a simple project manager or decision maker to just understand how our system performs. Most of the people who are operating their system don't really understand the capacity of the system performance. And so starting with very simple perturbation is a really good first step. We are lucky in California to have all the technology and information and resources to be able to get more advanced information. And that's where we're heading with the Trelawney study. Jim, you want to add anything?
No, I mean, we're just, one of the things we've observed with water managers in California is that they understand the mechanisms of climate change. They don't understand their actual vulnerabilities in a numeric kind of quantitative way. And so we think that this approach allows us to describe kind of a risk-based sense of the performance of their system currently, and then it also allows us to explore adaptations and describe the performance of those adaptations in a risk-based measure of performance.
Thank you for that. We have another question, and I will ask it to you, but I also maybe open it to some of the other colleagues on the call. For example, the one that Roy mentioned now, he says, thanks for the presentations. How can we relate climate change, adaptability, and vulnerability with the demographics and livelihoods?
Yeah.
So we are including, and I didn't mention this in the list of models. We do have also an economic model that's describing economics related to flood, water supply, ecosystems, which is challenging to quantify economically, but the state is improving in that area. And then a new area that we're really going to need to push is how to quantify groundwater sustainability. And there's some specific metrics that we're kind of daylighting as potential economic values for things like preventing subsidence, for example. So that has more to do with groundwater sustainability, but we are doing some groundwater, some economics associated with the performance of the adaptations.
All right, thanks for that. I'm not sure if John, you want to add something, Matthews?
Thanks a lot. I appreciate that, and this is a fantastic presentation. Roman and James, I'm really grateful for that. So the question, I think it was that was just on, I think is accurate, in that many of the cases that we presented in the course tend to focus much more on both kind of precip and temp variables and economic impacts. But the beautiful thing about the language of performance indicators is that we can measure performance in lots of different ways, not just in terms of economics. And some of the work, for instance, that we did in Mexico around environmental flows, and looking about risks there, was to define performance indicators that were about reaching what biologists refer to as ecological drought conditions, which is essentially when an ecosystem has had enough water withdrawn from it that it reaches a kind of tipping point of irreversible and potentially catastrophic change. So being able to think about a performance limit that's based on a completely non-economic variable is actually a really useful component. You can imagine that maybe in this case, for instance, just brainstorming, speaking completely off the cuff on a project that's not mine and that I have no influence over. One of the performance indicators that could be of at least indirect interest is the rate of groundwater recharge. If that was something that could actually be calculated, and that might be a kind of rate limiting step that's important to be able to track in terms of a potential. So again, a totally non-economic framework and variable, but one that's really essential to the approach of the process. So I think in many cases, if we want to get avoid that sometimes trap of assigning economic value to ecosystem services, that these kinds of ecological performance limits are probably a really good framework.
Mm-hmm.
Yeah, I would like to add to John on that. I think it's our experience with the Trelami is that we're looking at the multi-sector aspect, and for the water supply, the Stillwater project, because we're looking at water supply, we have a set of metrics that, it's a given. People are familiar with them. They live, dream, eat with them. And so it's pretty straightforward. But when you start to look at, water supply, ecosystem, and flood altogether, your number of metrics can really quickly explode. And the other aspect, which is tricky, is depending on who you're talking to. A reservoir operator set of metrics will be totally different to the decision maker. And decision maker may think about, a year, 2 year, or like the 2 year drought. The reservoir operator is going to think about, what is going to happen tomorrow. And so there is also like this dimensional aspect, which is tricky. And I believe that engaging the stakeholders really early in the process and make them part of the discussion early on is really key on selecting the metrics and figure out, what are the key. After you never say, if you may, when you're starting to do your analysis, you may find some, response from your system that you may not have expected. And so you need to be also flexible to be able to change your metric depending on what you find out from your system.
I think that's a great observation, Romain, and that's exactly right. That these trying to define these useful variables ideally should emerge from your talking with stakeholders or kind of core partners in the process. Sorry, I didn't mean to interrupt. I think that was Koen.
This is a great conversation. One of our challenges in California is we're trying to convince folks that it would be better for them to understand their watersheds because that allows them to understand that there's going to be vulnerability to water supply and to flood and to ecosystems and to groundwater, and everything's connected. Getting everyone together to understand they're all vulnerable. They're vulnerable in different ways. Water supply more vulnerable to droughts. Flood more vulnerable to, in California, to atmospheric rivers. But then beyond that, ecosystems are definitely vulnerable to climate change, and we're trying to describe that in a more clear way. And then groundwater, of course, because a lot of water management in California is really focused on that right now with the new emphasis on groundwater sustainability.
Thanks for that, Jim. We of course are over time, I know that, so we'll just keep another 15 minutes maximum for further conversations, both on CRIDA in general and on the presentation. I think we covered most questions, but we have one hands up from one of the participants, so we'll just give the floor shortly to Israel and Soro to see if he could ask a question directly to the participants and the panelists. Go ahead, Israel. I'm not sure if he can unmute, so I'm going to try from my side. If not, I'm going to just give it 1 minute more to see if he can speak. It may be challenging due to technical issues. So while we wait for that, we just maybe go for the next question, which is a bit more generic to CRIDA. And of course, many of the questions we received are related to the course training and to CRIDA in general. I think there were quite a lot of questions about the scale of application. I think there was a question about, can we use CRIDA for small basins like aquifers or only for big basins? But also, how can we use CRIDA for transboundary systems? Does it depend about national administrations, regulations, policies? And maybe in the same setting, a question about, can we use CRIDA for urban or rural areas? And are there important differences? So I think with that, we have a bit more of generic questions about the applicability. And maybe I would like to invite some of the panelists, and here's a few of them mentioned, but there's actually many more on my side. So please provide your feedback, colleagues.
This is John. I can jump in on the transboundary question.
Sure, go ahead.
Thanks, Koen. So one of the largest CRIDA projects that I'm aware of actually is in transboundary basin. It's in the Dniester basin, which is in Eastern Europe, Ukraine and Moldova, going into the Black Sea, and it's a geopolitically a very sensitive basin. This was a project that was led, I think, on a 20 million euro budget by the UN Economic Commission of Europe with support from the US Army Corps of Engineers. It's a very interesting case study. It's focused, it's a multi-year project. It must be in its last year or so now, looking at flood risks, and especially a lot of the actions that were performed on the Ukrainian side, the upstream side, were exacerbating flood risk in southern Ukraine and in Moldova. So that a lot of the performance limits there are around flood return periods and damage situations. If you reach out, I can put you in contact with the team at the UNECE and the Army Corps that were involved in the analytical work. It's a really good process. It actually was connected to even the signing of a transboundary agreement, water sharing agreement between the two countries.
All right, someone else wants to comment on these different scales and focus areas?
Yeah, the challenge is, it's I think there is not a fit-all kind of scale. In California, we work directly with the Stillwater project, which is pretty much covering the whole states, and so the scale is very large. And the thing which is nice is that we only engage one stakeholder ourselves. As soon as you start to try to look at the watershed base, or like a basin like the Sacramento or San Joaquin, you have many players to deal with, and that starts to be very tricky to your engagement and communication start to bubble, because you want to try to do your best to accommodate everybody. And so that's why in California we're pushing this watershed base scale, which is like a little bit smaller than like this basin scale. Because you may only need to deal with a couple, or work with a couple of stakeholders, and make it more easier to work together to come with consensus on how to move forward. Again, the multi-sector aspect had another difficulty. You need to bring the water suppliers with the NGOs, and they have conflict interest. And so again, making sure that they understand how the system performs upfront is key. And that's where I think you can come with consensus. And so the scale doesn't really matter, but it's really a clear communication that needs to take place.
All right, thank you very much. Maybe some examples that can be given about difference between rural and urban areas. Maybe some of the colleagues that have been involved in the Urantani case study, or some other work in, for example, Ecuador. But I'm not sure if colleagues from Delta Iris are still on the call. I can't see them. But maybe somebody just can explain a bit more about the Urantani case, where this is more of an urban situation compared to more rural area examples we have also covered.
One example is what the San Francisco Public Utility Commission is working on. I think Alexis Dufour gave I don't recall if it was a workshop or with Casey Brown a couple of weeks ago, or a couple months ago, I don't recall. But it was really urban orientated example, where they really focus on the demand and supply aspect. with the Turlock and the Merced study, we're definitely looking more into like both. We're looking at the urban aspect as well as the agricultural aspect. And when you think about the flood-mar adaptation strategy, flood managed aquifer recharge, so capturing flood flows to recharge groundwater, you need to work with like local entities and like farmers to make sure they understand the adaptation. And so I think the process is very similar. I don't see a differentiation about urban or agricultural process. It's a lot about engagement and communication up front and finding opportunities for all entities.
Thanks for that. Maybe just one quick question about pollution. We haven't really talked about that so much in terms of quality. And I think maybe, so does CRIDA cover, and it says incident pollutions. I'm not sure if it mentions ancient pollution or accident pollutions, but it could be either. And also I think some people were raising some questions about if water quality is actually a driver or if it's a performance metric, because in some cases, of course, it could be both. And if that has been taken into account in some of the case studies. So I'm not sure if either you have been looking at pollution as one of the issues.
So pollution, in California, we have the CEQA, NEPA requirements, which is like, the greenhouse gas emission. And so every time that you're going to move forward with like the implementation of a project, you will need to identify the greenhouse gas emission and your impact. And so it's to me, it's not, the pollution aspect is not taking into account until like, the implementation of the project. However, the water quality aspect is a big one. And we recognize that in California, we have, temperature requirements that we need to meet when we release water from our reservoirs. And with the increase on temperature in California, these requirements may not be met. And so that's going to be certainly like one of the future topic. We're doing one step at a time, and I think there is certainly people at Berkeley, like Ted Groundham, who is like thinking already about it on the water quality aspect, and also like our the other entity in the state of California is our State Water Resource Control Board, which is looking at like the water quality aspect, and hopefully at one point they will be able to tackle it.
Thanks for that. If no other colleagues want to join in on this one. I have another question then related to rapid change. So how does this approach particularly deal with rapid change? And how does it allow for conditions where, although there may be uncertainty, but when change actually occurs rapidly or has major consequences? For example, whilst the models might show outlier scenarios as being unlikely, the reality might be on the high risk and high consequence spectrum and happen much sooner than modeled. So I think that refers to more about we're doing planning, but are we also looking at monitoring at the same time and tracking if those extreme events we're looking at are happening sooner than we're expecting, and if they can be used to maybe upscale some decisions faster or address emergent issues.
I don't want to take the answer away from Jim, but I think, what we're doing with flood-mar with the 3 different levels of implementation is really in this concept of, we cannot just go ahead and build a $2 billion adaptation strategy. And so you need to be gradual, and our investments need to be very strategic. And so by evaluating like 3 levels of flood-mar, a level of 1, which is just using the current infrastructure, a level 2, which is going to require permittings, like discussion with our federal colleagues to modify rule curves and operation, and then a level 3, which is really more the construction of like new facilities. We hope that we we are not slowing down the process, but we are progressively increasing our capacity to adapt. And there is low-hanging fruits that we can use right away on, who are easier in the permitting process. And there is other adaptation strategy who are going to be more tedious because they will require many more permitting requirements, will take times. And I mean, that may not be the case in other countries, but in California, that the permitting process is definitely something that takes time. It cannot be resolved, quickly. I don't know, Jim, if you want to add on that.
No.
You need to unmute yourself.
That's good. I was thinking about, we're just starting to think about getting to a discussion about solution pathways, and thinking about, are there critical points as we move into the future where water managers are going to have to think about making some significant decisions, maybe some significant investments, or changing the way they think about managing their systems. And this will definitely allow folks to think about, okay, what are those thresholds that as we're seeing us moving in a certain direction, what are the thresholds that we need to keep our eyes on for, if we get to a certain point, we're going to have to make, substantial changes to the way we operate our systems.
This is John, and I might also add that that this is one of the topics that is really worth considering in step one when you're thinking about the decision context. And often as you get into a project, you may need to go back and really kind of make some adjustments in how you define the decision context as you discover that there are maybe there's another kind of administrative chain of command or a critical stakeholder that you were not aware of, and that it might adjust some of your how you're considering what the parameters are for success and failure even. And I think what you're hearing from James and Romain is really that sometimes, especially when we're thinking about kind of interacting with a complex bureaucracy, which is completely normal with a large project, is that it will end up adding some extra time to the process. And so that it might, as you move into the step where you're beginning to define particular pathways, often you need to almost insert spacers to allow these different bureaucracies to actually be able to absorb and process the information. So in Western Europe or in North America, like a large piece of infrastructure, like a really large hydropower dam or a large storage facility or a big utility, it can take 15 years. Which I think is probably unusual for a lot of middle and lower income countries, but it's just really a kind of a reflection of the complexity of our bureaucratic processes and the number of governance levels that you're interacting with. So those kind of spacers are important to be able to kind of include in your ultimate process.
Thanks for that, John. Maybe I think we could start finishing off. Maybe one small last question before we do the wrap up. So there's one question about water salinity. So I'm not sure if in the case of California that has been an issue so far, and maybe if not, John can maybe give some feedback on using salinity as an indicator.
Well, on the Stillwater project, we have, because the water is moved from northern side of California to the southern side of California, we're going through the delta, and the delta is a mixture of like saline, clear water, and with sea level rise, the operation in the delta may get affected. In fact, one of my colleagues at the Delta Stewardship Council will release soon a vulnerability assessment, a much more detailed vulnerability assessment looking at like broader range of sea level rise to see at what point the system need to push more water to clear it enough to send it down south. And for sure, that's, you know, one of the biggest challenges. In fact, in California, to remediate again this salinity issue, we are moving forward with a big project of tunnels through the delta to be able to try to like continue to meet the environmental needs as well as our export down south. So and not get impacted by the salinity intrusion into the delta. And I can send more information if people are interested.
Thanks for that. I think with that, we could probably close this Q&A session. So I'm just gonna wrap up because we're already half an hour over time, and I think the idea was to keep this to no more than 1 hour and 30 minutes. So just maybe to thank the speakers, specifically Romain, Jim, even under these very difficult conditions that you were able to join us. I think it was very, very welcomed, and thanks for that. But also, of course, our colleagues from Deltares, Agua, and US Army Corps of Engineers, as well as some of our other colleagues that have been supporting the questions and answer sessions and addressing some of the remarks. Maybe I can just finalize with referring to the current course, which of course still is ongoing for another 2 to 3 weeks. So we of course are available for further questions in the let's say exchange discussion forum. We are aware that somehow we may be a bit delayed in answering some of the questions, but we of course will make sure we go through them before the end of the course. We also see the need maybe for having a follow-up activity, and I think some of the questions were related to another case study that was developed for the greater city of Mexico. And I think that also would be interesting to maybe have in a follow-up activity or webinar, as well as maybe thinking about alternative elements that CRIDA could take on board. And as you see, every case study is different, and new knowledge and concepts are emerging from that experience. So we also see the need maybe to host another webinar just about a brainstorming session around some of those concepts that could find their way in an updated version of the CRIDA approach going forward. As you know, CRIDA has been around for a while. It was published 2 years ago, but already it was being used quite a longer time before that. So of course, over time, new elements are emerging, and I think it's also interesting to explore those further and see how they can bring value to the approach going down the road. So I just want to thank you all for your contributions. I think it was a very interesting and interactive session. And we will, of course, make sure that this recording is available to all course participants, and we probably make it public so that other people interested and not necessarily part of this course can also access this, this webinar. So just thank you all for your patience and to be with us a bit longer than expected. And we hope to see you in the course or in the next webinar that will probably come just after New Year. Thanks to you all, stay safe, and we hope to see you soon. Thank you.
Thank you.
Thank you.